Today is the day that we are going to connect roots, zeros, and polynomial graphs. Yes, we're going to figure out how the behaviors, that is the end behaviors and all of the turning, connects with what we know is a root or a zero. Now, if you're saying, but I don't know what a root or a zero is, well, hang in there because we're going to find roots and zeros, and you're going to see that they connect to polynomial graphs. Now, if you have a colored piece of paper, just piece of paper, you might want to fold it into 4 sections. I don't know if I'd make this middle section quite so big. We are going to write some stuff in there, but I would make it just a regular size. But I'm going to kind of give you that title partway through the lesson. So let's begin, because there's like a sort of pattern. There's something to notice when you start with an equation with just an x, or as you'll say, x to the first power. Like, how about p of x equals 5x plus 3? Now you say, well, what are we going to do with p of x equals 5x plus 3? Well, what have you already learned about it? You've learned things about its end behavior, right? You know that because the degree is odd, that the end behavior is going to go in an opposite direction. And continuing, you know that since the leading coefficient is positive, it's going to go up to the right, but then, of course, opposite direction down to the left. But how does this connect? Well, the answer is it connects very nicely with what we would consider or call the zeros. Now, the zeros are when you set the equation equal to 0. You know, like solve the equation. Subtract 3 from both sides. Divide both sides by 5. That was pretty easy to do, but we call negative 3/5, we call that the zero of the function. And what does negative, or how does negative 3/5 ultimately show up on your graph? Well, it shows up as a root. And remember, a root is just an x-intercept. So remember, we knew our graph was going to go up to the right and an opposite on the other side. Well, then there's only one way to connect the dots, and that is to pass through the root. And when you pass through the root, you're able to connect the end behaviors of that graph. Now, this particular problem, notice, again, it only had one root. It only had one zero. But what if we have an equation that is to the second power? You know, a degree 2, that we call a quadratic equation. Well, let's see. What would happen with negative 2x squared plus 8x plus 12? Let's see what happens if we solve this problem. You say, what do you mean solve this problem? Well, we're going to solve it for the zeros, and the zeros are simply when the equation is equal to 0. Now, when I look at this equation, I see some things that we studied about a month ago. I see something that maybe could be factored, like factor out a GCF. Now, if you carefully factor out a GCF, you're left with x squared minus 4x minus 6. Of course, that is still equal to 0. Next, maybe if I'm lucky, I can continue to factor the problem, but it turns out that, well, I'm not so lucky, because there's not 2 numbers that multiply to be negative 6 and add to be negative 4. Now, does that mean that I made a mistake? No, it just means that I'm not able to factor the problem. But there's another way to solve this problem. It's something else that we learned about a month or so ago. It's called the quadratic formula. Now, if you do the quadratic formula, which remember is the opposite of b, plus or minus the square root of b squared minus 4ac, all over 2a. I know it's a little bit of work, but if you do the quadratic formula, by the way, I'm doing the quadratic formula with my factored trinomial. You'll notice that the negative 2 is not really part of this quadratic formula. Instead, I'm choosing to use the simpler, smaller numbers, because it's easier. It's easier to do this multiplication, squaring, and eventually adding 16 plus 24 to be the square root of 40. That is 4 plus or minus the square root of 40 all over 2. Now the square root of 40, remember, kind of off to the side, the square root of 40 is the same as the square root of 4 times 10. And because 4 is a perfect number, I'm able to pull that out as a 2, left behind root 10. So the problem can simplify a little bit to be 2 root 10. That is 4 plus or minus 2 root 10 all over 2. Then I can do a little heart method to further simplify to be 2 plus or minus root 10. Now, got a little trickier here, but I had to use the quadratic formula to be able to solve for the zeros. But we're supposed to be making a connection with the graph. Now, if you think about this graph, you should say that because the leading coefficient is negative, that the graph is going to go down to the right. The graph is going to go down to the right. But because the exponent or the degree is even, it's going to have to be the same on the left. So the question again becomes, how do I connect these? Well, you connect them with the roots. Now, what are the roots? 2 plus or minus root 10. Now, that's not 2n root 10. That's 2 plus root 10. Think about it. 2 plus root 10 would have to be a positive number. And it's 2 minus root 10. 2 minus root 10 turns out to be a little negative number. Well, if I think about a graph that's going down to the right and also going down to the left, the only way to connect this graph is through the roots. And when I go through the roots, I end up with a parabola that's opening down. And again, has 2 roots. And just for one final connection, it actually has a y-intercept, that is this number 12, that actually fits and matches, which is nice. Basically, I know that my graph is right. Well, it looks like that when we have a polynomial of degree 1, that is x to the 1, we got 1 root. When we have a polynomial of degree 2, the one that we just did, we got 2 roots. So what's going to happen if we have a polynomial of degree 3? Do you think we'll get 3 roots? Let's see what happens. I'm going to give you a polynomial, x cubed, x squared, minus 20x. X cubed, x squared, minus 20x. What we want to do is we want to find the roots, or the zeros, and we want to make a connection with the graph. Now, again, how do I find the roots of the zeros? So I have to set the equation equal to 0. And when you set it equal to 0, you have to think back about a month ago. You have to think back and you have to say factor. Now, in this case, I can factor out a GCF. But then it looks like that my trinomial, my x squared plus x minus 20, it looks like that can actually factor because there's 2 numbers that multiply to be negative 20 but add to be 1. And those 2 numbers are plus 5 and minus 4. Now remember, this equation is equal to 0. So what I can now do is I can find the zeros of each one of these little factors. This one is kind of easy. It's just x equals 0. But remember, this one, let's change the color here actually, is x equals 0. The next one, though, is actually x equals negative 5. And then the last one here is x equals 4. Now, those are called the roots. And roots are the same as x-intercepts. So it should be the case that 0, 4, and negative 5 are going to show up on my graph. My graph that has a positive leading coefficient. Now remember, if the leading coefficient is positive, the graph goes up to the right. Since the degree is odd, we know the graph's going to do the opposite to the left. So how am I going to connect my 2 n behaviors? Well, through the roots is the answer. And as I go through the roots, we'll kind of pretend that one went through. I find out that my graph that it connects, that it makes sense. And it appears that because we had a degree 3, again, degree 3, that we ended up with 3 roots. Well, we have just discovered a little theorem. Do you notice the theorem? The degree is going to have everything to do with the number of roots. If the degree is 1, 1 root. If the degree is 2, 2 roots. If the degree is 3, 3 roots. Well, this is such a major idea in mathematics that we name it the fundamental theorem of algebra. This is actually the title for your little notes sheet. I didn't make this up, okay? This is the fundamental theorem of algebra, so named as it is basically what ties all of algebra together. And what's the fundamental theorem? It basically says that the degree will be the exact number of roots. Technically, we call that the nth degree. Again, the nth degree just means whatever the degree is. It means that your polynomial will have n. It will have exactly n roots. Now, it might have been it would be a neat idea to at least look at one of these graphs, maybe like the last graph that we just did, to look at something like that on Desmos. So I'm going to flip over to Desmos. You're welcome to open it up if you want to. We're going to type this equation in and see if it really does look like the one that we drew here. Okay, so the neat thing about Desmos is you can type y equals, you can type f of x equals, you can type p of x equals. I'm just going to kind of stick with the original y equals, and I'm going to go ahead and put in the last polynomial that we did, x cubed, x squared, minus 20x. Now, when you see these graphs on Desmos, you have to understand that sometimes they might be stretched out or perhaps in a little different scale than what I sketched. We can kind of fix it if we want. We can make the x-axis usually just be between like negative 10 and 10, but the y-axis needs to be stretched a little bit. You can see here that we seem to be from negative 30-something to 50-something. But how does it look? Yeah, it looks a lot like the graph that we sketched. And the truth is, that's because the fundamental theorem is always true. It's going to tie these graphs together with their roots and behavior. Let's look at an equation to the 4th degree. Let's look at an equation to the 4th degree now that we know that the total number of roots should match this degree. I'll provide you with an equation about x to the 4th, 5x squared, and minus 36. X to the 4th, 5x squared, and minus 36. Now remember, according to the fundamental theorem, the degree is going to, the degree, again, the nth degree is going to give you the total number of roots. So that means that we should end up with 4 roots for this problem. I wonder what will happen if we graph this problem first. Maybe we can kind of see those roots. What do you think? Yeah, let's again switch over to Desmos and we'll quickly type this in and see what we see. All right, so we need x to the 4th plus 5x squared minus 36. Wait a minute. If you look at this graph, it seems like we only have 2 roots. Speaking of roots, one of them looks like it's at 2, and one of them looks like it's at negative 2. Now, if we zoom out a little bit, it's not like we're missing like some of the graph like it's supposed to be somewhere else. It definitely is the case that we only have 2 and negative 2. So wait, what's going on here? I thought we just said that we were supposed to get 4 roots. Well, don't fear, child of mathematics. The fundamental theorem is still going to be true. Yep, we're still going to end up with 4 roots. We just need to go back to the equation and dig a little deeper. So I already saw the graph, but let's go back to the algebra. Let's solve this thing equal to 0. Now, perhaps you notice that the equation is a little strange. It has an x to the 4th, and then it jumps to an x squared, and then we just have the number minus 36. It actually can be factored. The reason it can be factored is because, believe it or not, there actually are 2 numbers that multiply to be negative 36, but add to be 5. Now, those 2 numbers end up being plus 9 and minus 4. But you can see that I used x squared and x squared because that's what's going to multiply to be x to the 4th. And because I have these x squareds here, I'm actually going to be able to achieve my 5x squared, since each of these distributes is going to get that x squared attached to it. Now, stick with me because we're not done factoring. We're not done factoring because x squared minus 4 actually factors into x plus 2x minus 2. Remember, you always want to fully factor the problem so that you can solve it. Now, when we say solve it, we mean solve it for the roots. And, I think I've seen these numbers before, negative 2 and 2. Okay, that's a good sign. Those are definitely the roots that were on that graph. What about this x squared plus 9? Well, be careful. Don't tell me that the answer is negative 9 or something like that. Instead, let's actually solve x squared plus 9. Like subtract 0. And let's make that look a little neater. And when you get x squared equaling negative 9, take the square root of both sides. Hold on a second. I thought we couldn't take the square root of a negative number. Well, you can't unless you're thinking of imaginary numbers. So I do get plus or minus. Remember, you always get plus or minus when you take the square root of both sides. But now I can describe this as an imaginary number, especially because that negative, it pops out to be the letter I. And when you take the square root of 9, you get 3. Put it all together, we get plus or minus 3i. Now, kids, I'm not making this stuff up. Plus and minus 3i is technically 2 roots. Count them, 1, 2. And then I have 2 more up here, 3, 4. Yep, I get 4 roots. Now, it doesn't matter that they don't all show up on a graph, because the truth is, the only ones that are going to show up on the graph anyway are going to be your real roots. Your real roots are 2 and negative 2. Again, my graph matched with that. My imaginary roots, plus or minus 3i, they're not going to show up, but they still count. They still count as part of my 4 roots. And so the fundamental theorem is satisfied. But we also learn that real roots are going to be x-intercepts. Again, not imaginary roots, but only real roots are going to be x-intercepts. That might be something that you want to add somewhere on your notes paper as we continue to learn about this fundamental theorem. I realized that I forgot something that would be helpful. If you go back to the original problem, we can see the y-intercept. Remember, the y-intercept's always that number at the end. Simply, it's a negative number, and that looks a heck of a lot like the y-intercept that's on this graph. So that's good. That's good. I know that my graph is right. Can you put it all together? Can you solve, graph, and connect all the behaviors for say, this polynomial? Well, that's the spot we're at. We want to be able to put this all together. Can you solve, graph, and connect all the behaviors? Now, I'd like you to say, yes, Ms. Naylor, I can, or at least, yes, I will try. But what do you mean solve? Well, you're always solving it equal to 0. That's because those are going to be the roots. Roots are always what makes the equation equal 0. So how you doing? Are you ready to solve this? Doesn't look like a problem, exactly like a problem that we did today, does it? You want to be thinking factor by grouping. Grouping. Factor by grouping. When you factor by grouping, you can pull out an x squared. You can pull out a -9. What do you think? It's looking good, right? This is the way it's supposed to work out. I get it. My x squared minus 9 and my x plus 4. Okay, now those are equal to 0. So then each one of these, x squared minus 9, that's perfect. I can actually break that down again. I can break it down into +3 and -3. Yes, go ahead and do that. Now I actually end up with 3 factors. Now when you solve each of these and you find -3, 3, and -4, you have just found what's called the roots. There's 3 of them. Oh good, there were supposed to be 3 of them, right? That's what the fundamental theorem says. Can you tie this all together with a cool graph? Notice I'm putting the roots on as the x-intercepts. It's really a good thing to do first. Next, I'm going to be thinking about the leading coefficient. The leading coefficient's positive, so I know my graph has to go up to the right. How about the degree? The degree is odd, so you know that the graph is going to go down, or that is, it's going to be the opposite to the left. It's going to be the opposite of going up, so it's going to go down to the left. I feel like you've kind of seen a problem like this before. Well, it's pretty common, pretty sort of standard polynomial. The only way to connect the ends is to go through their roots. We are in business. This is the way the polynomial problem works. So, the fundamental theorem, nth degree poly, it's going to have exactly n roots. But remember, only the real roots are going to show up on the graph. We'll talk a little bit more about those imaginary roots in the next lesson. But for now, you can take a look at the half-sheet homework.